Sun goes down, my eyelids close. I am learning, so it goes. There's hope around, I'm grasping tight. Can you hold me in the light? I don't.
This feast, it better be fancy. When I say fancy, I mean schmancy. Put on your tuxedo pantsy. Hard food, don't romance me. This feast, it better be fancy. Oh, it better be fancy. Winner, chicken dinner. Won't you change my kitty litter? This feast, it better be fancy. Oh, it better be fancy. This feast, it better be fancy. Oh, it better be fancy. So keep your kibbles, keep your bits. Don't you make me beg for it.
Don't you make me beg for it. Don't you make me beg for it.
This feast, it better be fancy. Oh, it better be fancy. This feast, it better be fancy. Oh, it better be fancy. This feast, it better be fancy. Oh, it better be fancy. This feast, it better be fancy. Oh, it better be fancy.
Yes, yes.
I won't eat no store brand. Let me help you understand. Oh, it better be fancy. Oh, it better be fancy. I will bite the hand that feeds me. Keep your chicken of the sea. Oh, it better be fancy. Oh, it better be fancy. You can shake that bag till the cows come home, but you will be sleeping alone. Oh, it better be fancy. Oh, it better be fancy. Oh, it better be fancy. This feast, it better be fancy. Oh, it better be fancy.
Yes, yes.
Oh, it better be fancy.
Yes, yes.
Oh, it better be fancy.
Let's move to a ghost town where we can visit with our friends. Let's move to a ghost town, Sunday dinners with our kids. When we move to a ghost town, no need to pack our things. I guess you'll have to see. No time for small talk, no need for pleasantries. It doesn't matter what you did today, and no, I don't care about your week. No, I don't care about your week. we move to a ghost town, we'll start a ghost family. You'll find the mind can wander when you ain't dwelling on mouths to feed. So we can move to a ghost town, or we can stay in the city. But I got my bags packed, I still got some cards up my sleeve. Let's move to a ghost town. Ooh. Let's move to a ghost town. Ooh. Let's move to a ghost town. Let's move to a ghost town. Let's move to a ghost town. Ooh. Looked at me like you couldn't see how cause leads to effect. You looked at me all nonplussed, could not believe I would reject your advances, all your blackmail and your empty threats. Like I was sand that would slip through your fingertips. Then you said, come to me, like I was on payroll. talked to me like I was a wild and starving animal, prone to her fits and rages, with aggressive tendencies. You know, the usual aggressive tendencies. Walked away from me like it was so easy. I looked at you like I could will you to want me. Turn around and change your mind. Just turn around and change your mind. Spinning my web as fast as I can. You keep breaking my home with your head. You are far bigger than me, but you're the one that's scared. I catch what I can. I only eat the things that land in my web. You take what you can and call yourself a grass-fed vegetarian. Say goodbye to the birds and the bees. Say goodbye to the trees. Say goodbye to the homes that you've known as people flood the cities. Well, the birds keep building their nests and the bees keep trying to make honey us. I've been spinning my web as fast as I can, but you keep breaking my home with your head.
Hello and welcome to another virtual science pub with us at OMSI. My name is John. I work in the marketing department here, and I will be your host tonight. But before we get started, I have a couple things to tell you about all the cool things going on at OMSI these days. So you may or may not know, but we are committed to sparking curiosity and igniting imaginations. Wonderful copywriting, I might add that myself. And to help everyone out at home, we've put together all sorts of engaging science activities and experiments to inspire you to experience the wonder of science right from your home or from wherever you are. So if you go to omsi.edu, it says Science at Home. It's a little section down there. There's videos, there's DIY projects, there's all sorts of great stuff that you can do. And if you do any of these projects, we would love nothing more than for you to share them, send them to us on Facebook or whatever you use, because we always love seeing people have fun doing science. Okay. OMSI is open. We are partially open, but we are open. You can come and join us. Our newest featured exhibit is called The Life and Legacy of Genghis Khan. It opened on Saturday. It's all about Genghis Khan, the Mongols, 13th century Mongolia, also Mongolia today, and a little bit about genetics. So it's a really fascinating look at that period in history. As we also have the USS Blueback submarine that you can come tour. We've reopened the Natural Science Hall. So you can come and visit with our little critters and bugs, and I think one of my favorites are probably the Madagascar hissing cockroaches. They're pretty cool. We also have the planetarium is open, and we actually have upgraded the HVAC system to include a new ionization system. It sounds cool, and it is cool. I can't tell you why it's cool, but it is awesome for keeping that air really, really clean. In fact, one of the shows that you can see there is called Dark Universe, and it's all about dark matter. I've seen it a couple times myself. It's super fascinating. So if tonight's topic interests you, you should really consider checking that out. Okay, there is something that you can do to put the pub back into Science Pub, because as you may or may not know, we used to host these here, at the museum. We would host them at different restaurants and places. So this is a way that you can help support your local community. We have some wonderful food and beverage partners that we partner with. And I would encourage you, if you're looking just to get a couple good beers or a tasty burger or something, this slide has all the information with some of the partners that we work with. They are wonderful, and I highly recommend you get something from them one of these days, because they taste delicious anyway. Okay, let's talk schedule real quick. So if you've watched a Science Pub with us before, this is pretty similar. If you don't know what a regular Science Pub looks like, we're going to start with some dark matter themed trivia. That's where we'll bring on a guest, and we're going to do just about 10 questions just to kind of get everyone's dark matter brains warmed up. So make sure to have a pen and paper or your iPhone or something to take notes on there. And then we'll have about an hour lecture from our presenter, Dr. Yu. Now, for the Q&A, you can submit your questions at any point during the lecture via the comments in our live feed. We'll collect them all after the lecture, and I'll mediate the Q&A with Dr. Yu. So just send us your questions as they come up, and we'll do our best to address them at the end. And then, of course, if you enjoyed tonight's lecture, we always are grateful for donations, and so that's a big help. But don't worry, you know what? There's no pressure. We just want you to sit back and relax and enjoy all the science we're going to give you here for the next hour and a half or so. So let's get ready. Okay. Trivia time. Everyone, time to bust out your notepads, your pens. This week, we have one of our outstanding educators, Rebecca Riley, joining us to play along live with you at home. She's an educator with our teen and adult education programs. Everyone, please give a virtual or real round of applause to Rebecca for joining us. I am clapping on behalf of everyone watching right now, Rebecca. Okay.
Thank you.
So just a little thing. So maybe everyone at home, make this a little interesting. Maybe put some skin in the game. Maybe, who has to do dishes next, play to see, who gets to take out the trash. You never know. Just make it fun, mix it up a little. What we're going to do, there's going to be 10 multiple choice questions. So I'm going to read a question. Rebecca is going to work her way through it, and along with everyone else, and then we'll reveal the answer, and we'll move on to question number 2. Okay, Rebecca, are you ready for dark matter?
I'm super ready. I'm even wearing a space hat that I got from OMSI.
That is already a leg up. You're already ready.
I'm on brand in multiple ways right now.
And your dark sweatshirt. Okay. So this is probably just a question that I would just ask in general. What is dark about dark matter? Is it A, it absorbs light, B, it exists in outer space, C, its only significant interactions with us are gravitational, or D, it appears black in telescopes?
So I feel like black holes are the things that absorb light. A lot of things are in outer space.
Yep.
I don't really understand C super well because I'm a biology major. So I'm going to go for D. It appears black in telescopes.
It appears black. Okay. Ooh, C. It was the one that you didn't understand. I have a feeling we're going to learn more about this question.
I need to learn why gravity is dark. Yeah.
Hey, and just so you know, I do have, I've got a few jokes and a few puns ready for this trivia. And I will say that
have you said them yet?
Well, I was just going to say that physics puns are no joke. They are a relatively dark matter. Oh, man.
I hope there's a sound effect.
Yeah.
Put on for that. Like a whoop.
The wah, wah sound effect. Okay, number 2. How many neutrinos, a small subatomic particle, and quite cute when it puts on its bonnet, might I add, are passing through your body per second? You have a whole bunch of numbers with ones and a bunch of zeros as your possible answer.
I'm going to go for 100 million because it's a lot, but not the most lot.
Okay, 100 million. Ooh. 100 billion. Whatever. There you go. So now we know what the neutrinos are. And, I don't know, I personally don't know, maybe we can ask Dr. Yu if a neutron and a neutrino are similar. But I will say I knew a neutron. He walked into a bar and asked for a drink, and the bartender looked at him and said, "For you, no charge."
I feel like that would also be true if a neutrino came in. It might be asked for its ID first.
Maybe it's a little baby neutron.
They're also neutral.
Okay, number 3. What contributes the most to the total density of the universe? Is it A, normal matter, B, dark matter, or excuse me, B, dark energy, C, dark matter, or D, neutrinos?
I already forgot what neutrinos are, even though we just saw their definition last slide. I'm going to go for dark matter because matter has density. Energy doesn't have density, does it? I hope not. Let's go C.
C, dark matter. Okay.
No, energy density. I hope I'm making everybody at home feel very confident about themselves.
Yes.
Who's getting all the things only a little bit wrong.
I will say when it comes to when you're looking at the entire universe, I will say this, just don't trust atoms because they make up everything. Or maybe not.
We're only on question 3. Do you have 10 more? Do you have 10 puns? Do you have one for every question?
Becca, I'm always prepared.
Okay, good.
After dark, question 4. After dark matter, most of the mass in our galaxy is it A, stars, planets, gas, or supermassive black holes? A great song, by the way.
Are you talking about black hole sun?
No. Black hole sun was Soundgarden or Stone Temple Pilots. Yeah. And then supermassive black holes is Muse.
Oh, okay. You're getting on the newer music. Okay. Planets are super tiny, so I'm not going to go for that. Stars are also pretty small, but stars are made of gas. But gas is, I feel like I'm seeing the really blinking answer that says supermassive, and I should choose that. But I'm going to turn away from that bright blinking, probably correct answer and try to keep my streak of being almost right every time. And I'm going to say C, gas.
Ooh, let's see. Oh, stars. Hey, I mean, here you go. I mean, the Milky Way is so big. You know, I did, however, know a black hole one time. You know, he walked into a bar with a supernova, and the black hole says, "I'll have what he's having." Because a supernova exploded black hole. Anyway, I told my wife that joke, and she just kind of.
I was kind of listening, but I was also reading the answer, so I had a hard time multitasking there. I bet it was really funny though.
Here, I'll redo it because there's probably some people in your same position. A black hole and a supernova walk into a bar, and the black hole says, "I'll have what he's having." Because black holes suck everything in, supernovas.
Doesn't a black hole happen after a supernova? So the
Look, Rebecca, look, I'm not a scientist. I just find funny jokes that are somewhat scientifically.
I don't know if I can call myself a scientist either because I'm getting everything.
Well, you're a biologist.
That's what scientists do. Scientists usually get things wrong, don't they?
Which of the following astronomical discoveries has not earned a Nobel Prize? Is it A, dark matter, B, dark energy, C, cosmic neutrinos, or D, pulsars?
Well, the Nobel Prize this year was awarded to a woman for a black hole, but that's not an answer.
Well, this is one that has not.
Do you have it? Do you have a hint for me? Can I?
Well, we talked about dark matter versus dark energy before.
Yeah. Are you saying it's probably one of those because we talked about them?
I'm not saying that. But what I am saying is we kind of got a little confused on the dark energy versus dark matter, which I'm hoping Dr. Yu clears up for us.
This is true. I actually don't know what any of these things are. I'm going to say pulsars because that sounds cool.
Ooh, I love pulsars. But it is A, dark matter. Last one, it was dark energy, you know. However, you know, back in college, when the astronomy department found out their professor wasn't going to get the Nobel Prize this year, they threw him a party and gave him a constellation prize instead. So bad. Okay, number 6. Approximately what fraction of our galaxy is dark matter? 10, 50, 90, or 99%?
You know.
So this answer, I feel, is surprising, but not like, oh my goodness gracious, surprising.
I was going to say, I feel like there was a previous answer that mentioned, but maybe it was about the universe and dark matter. It was saying dark energy was like 60-something% and dark matter like in the teens, but that was the universe, not the galaxy. Am I like?
Yeah, universe is a big place.
50. I'm going to go 50.
See, close. 90% approximate. I think give or take like, you know, 1.
If only this would have been true for the whole universe when I chose dark matters.
Perhaps.
Really important back then.
You know, I couldn't find a tie for this one, but the question is still a good question. How many general relativity theorists does it take to change a light bulb? It's 2, 1 to hold the bulb and 1 to rotate space.
I like that one. I think that might be my favorite joke I've heard all night.
Nice. All right, good. 1 for 10 is good. I mean, I'll take it. Okay, number 7. Gravitationally bound masses of dark matter are called. There's some good ones in here. Dark matter blobs, dark matter spheres, dark matter halos, or dark matter clouds. At
this point, I kind of want to keep my 0.
Improve your biology roots.
If I was playing, is it Hearts? I would be shooting the moon right now.
You would. You'd be shooting the dark energy or dark matter.
I'm gonna go for dark matter blobs. Most fun. That's the most fun.
Oh, it's so good. It's actually dark matter halos. Kind of like the bright lights, you know, and when I think of light, I think of photons, you know, and then that photon that checked into a hotel and he's asked if he needs any help with his luggage. He says, no, thanks. I'm traveling light. Okay, number 8. What is the axion, hypothetical elementary particle, named after? So what is this hypothetical elementary particle named after? A character from a science fiction novel, a brand of soap, a chemical compound found in stars, or Frank Wilczek's cat?
I don't know who Frank Wilczek is, but I'm going to go with his cat.
I mean, that's usually what, I mean, if I were a scientist and I found something like that, it might be it. But apparently it is a brand of soap.
Why?
You know, I think there's a lot of scientific questions out there that start with why that we will never know. I will say this, though. Singing in the shower is fun until you get that soap in your mouth, and then it just becomes a soap opera. And it all falls apart.
Oh my God.
Oh, so bad. Quick, let's get this over with. Okay, number 9. Which of the following statements is
That one really got me, though, John. That really got me.
We talked about this. No cry laughing. I mean, you know.
Okay.
We got
I'm
to.
here. I'm ready.
Okay. Number 9. Which of the following statements is not true about quarks? It's a tiny particle made up of protons and neutrons. B, it was discovered in the Hadron Collider. C, it emerged just after the Big Bang. Or D, it comes in many flavors, including up, down, strange, and charm.
Okay. I feel like I know that D is true and B, and it makes sense for C to be true. So I'm going to say A is not true because protons and neutrons are a lot bigger than quarks.
I'm going to have to listen to this presentation because I am very out of my realm on this.
Oh my gosh. I'm every time.
There you go. The mystery
What?
arose.
Protons and neutrons make up a quark? I thought they were tiny. Okay. Well, that's cool.
I will, you know, there's always the standard, you know, what does a subatomic duck say? Quark. Oh man. Okay. Last question we have to put people through. Okay, this is good. True or false?
Okay. Whew. Okay.
Your odds have increased. Scientists have created dark matter maps.
I don't know what that is, but if you wanted to wink a certain number of times, I just for no particular reason, I say it's true.
It's true. All right. You know, and I gotta say,
quirks, a million tiny high fives to all the quirks in the rooms around me.
so many high fives. I gotta say though, I do love maps. I'd be lost without them.
I still think the soap opera one was your best joke tonight.
I know, that was a funny one. I like that one. Okay. As
Okay,
always,
thank you.
Rebecca, it is wonderful to see you. Thank you for participating in our science trivia tonight. Have a lovely evening.
Home. I hope I boosted y'all's confidence.
All right. Yes. I can't wait to see how everyone else fared through the trivia. Okay. Now I'd like to introduce everyone to our speaker. Tien-Tien Yu is an assistant professor of physics at the University of Oregon. Prior to arriving at University of Oregon in 2018, she was a fellow in the CERN Theory Group in Geneva, Switzerland, and a postdoctoral associate at the C.N. Yang Institute for Theoretical Physics at Stony Brook University. She received her PhD from the University of Wisconsin and spent 2 fruitful years of her PhD in the theory group at Fermilab in Batavia, Illinois. That is enough talking from me for now, so please everyone join me in welcoming Dr. Tien-Tien Yu. Take it away, Dr. Yu.
Great, thanks a lot, John. That was a fun and pretty tough trivia. Although I will have to say, I think the one about the quarks, there was a typo in the answer because Virtual was right that quarks are smaller than neutrons and protons. So it's actually the other way around. So in principle, she could have gotten two correct. So yeah, so I wanted to thank the organizers of this OMSI Science Pod for inviting me to come give this talk. because of the situation, and this is online, it would have been nice to do it in person, but I'm glad to spend my evening with you all talking about dark matter. So the title of my talk is Searching for Dark Matter, Uncovering the Mysteries of the Universe. So I wanted to first start off with a brief kind of intro about who I am as a scientist. So here on the left-hand side, I say that I am a theoretical particle physicist who studies dark matter. So we can go through each of these descriptors. So theoretical particle physicist means I'm a theorist, and I'm not building, well, this is not completely true anymore, but for most of my career, I was not building experiments. Instead, I was writing down models and coming up with ways to test different models and theories of particle physics. So particle physics is the branch of physics that is describing all the fundamental particles, which are the building blocks of everything we know about in our universe, as well as their interactions with each other. So I've put here a picture, like a diagram, that is from actually this movie Particle Fever. I think that's when they first came up with this this format for describing the standard model, which shows all the different particles within what we call the standard model of particle physics, which contains all the known particles that we know about and the force carriers. So these are, for example, like the photon is what carries electricity and magnetism. The gluon is what keeps protons and neutrons bound together as an object. And the W and Z bosons are weak force. They carry something we call the weak force. And then the Higgs boson is what gives all the massive particles within this diagram their masses. And this was a great discovery in 2012 that resulted in a Nobel Prize for this discovery. And the Higgs boson, part of the reason why it's in the middle, it was the last missing piece for particle physics. So all the other particles had been discovered starting in like the 70s or so. And up until 2012, the only missing piece for the standard model was the Higgs boson. And here in this diagram, we also see on the top half of it, so the up charm, top down, strange bottom, these were the quarks. So this was part of the trivia these quarks, and particularly the up and down make up neutrons and protons. And then the other quarks are a little bit heavier. They are important for other things. And on the bottom, we have a class of particles called leptons. And so the left-hand side are the tau, muon, and electron. And the right-hand side are their partners, which are the neutrinos, which we also heard about in the trivia. And fun fact about neutrinos, they are related to the neutrons in that they're neutral particles. And so when they were first discovered, it was discovered by an Italian, and of course he named them neutrinos because they were small neutral particles, so small neutrons. They're not really the same as neutrons, but it's kind of a cute little name. And so the last part of this slide is saying that I studied dark matter. So you'll notice that dark matter is not included in this diagram of a standard model. And that's because dark matter is a part of physics that is what we call beyond the standard model. So it's the standard model of particle physics cannot explain this phenomenon that we call dark matter. But we know that dark matter exists, so I'll explain throughout this talk why we as scientists believe that dark matter exists and why it's so interesting to study. And it's one of the big fundamental questions within particle physics is what makes up this dark matter. So the standard model describes everything we know, like what we call normal matter, baryonic matter. And dark matter is not part of this standard model. All right, so before I really dive into the science, I wanted to do a little pitch about some of the comics that I'm going to be showing in this talk. And so a collaborator and I at the University of Oregon, so Professor Catherine Kelp-Stebbins, who's a professor of comic studies in comparative literature at UO, and I started the Science and Comics Fellowship program. So our first iteration was this past spring. You can find more information about it at this link that I have on the bottom of the slide. And the idea here was that we would pair together scientists with a comic studies student, usually an undergraduate student, to make a comic about the scientist's work. And so I was one of the first scientists, so in the spring, I paired up with Mary Hubbard, who was a really fantastic art student. And we wrote a comic about dark matter, so you'll be seeing a lot of her work throughout this talk. And the other pair was Audrey McNamee and Luca Mazzucato, who wrote a comic about serotonin. So it's a neuroscience-themed comic. So if you want to see the fruits of their labors or our labor, I recommend that you check out this website. And currently there's another set of two pairs that are making comics. Also, I think they're both physics related this time, and we'll continue doing this throughout the year. So by the end of the year, we should have 8 comics that kind of highlight some of the science work that's being done at U of O. Okay. So let's get started talking about dark matter. So I want to kind of set the scene. So this is a nice comic page from Mary's comic. So the scene is, we know about the Earth. We live here on the Earth. Here's the top panel is the Earth. And the Earth is made up of matter that we call baryonic matter. So this is, for example, protons, neutrons, and electrons. These protons and neutrons and electrons combine to make atoms, then make up molecules that make up what we know of as matter. And the Earth is a planet that's orbiting around the sun. And all of the sun and all these other planets are also composed of baryons. Okay? So, and our sun is huge. It's much, much bigger than our planet, but it's also made out of baryons. However, our sun is just one star out of billions of stars in the Milky Way. And all these other stars are also made up of baryons. So all the stars in the Milky Way are made up of baryons. And the Milky Way is just one galaxy out of billions of galaxies in our universe. So we see we're slowly starting to build up in size. So we have a lot of matter that we're discussing so far. But if you were to weigh all of this matter, so I'll discuss in a little bit how we make these kinds of measurements, how we quote unquote weigh this baryonic matter, we can figure out how much mass of normal matter, baryonic matter, there is in the universe. And when we make this measurement, what we find out is that baryonic matter only makes up about 20% of the matter in the universe. So that means that the other 80% is something that we don't see, that we don't know about, and is much, much more than the amount of baryonic matter or normal matter that we understand, know, and love, that makes up everything that we know and love. So the big question is, what is this missing piece of our universe? What is making up this other 80% of matter? And so I'll go through these arguments in the next few slides. That scientists believe that this missing matter is known as dark matter. And there's many candidates for the identity of dark matter. So the first question you're probably asking is, what is dark matter beyond the fact that it's this thing that makes up 80% of the matter in our universe? So the first thing I do when I don't know what something is I go to the internet and I put it into Google. And so I did that with dark matter, and it took me to Merriam-Webster, which is okay. It's a reliable, I think a fairly reliable choice to find definitions of things since it's a dictionary. So I plug in dark matter into Merriam-Webster, and it tells me that dark matter is a non-luminous matter that's not yet directly detected by astronomers, but it's hypothesized to exist to account for various observed gravitational effects. So one thing I find a bit funny, maybe a little bit sad, also surprising, but I'm also a dark matter physicist, is that its popularity is the bottom 20% of words. So I use dark matter every day. I would say it's probably in the top 10% of my words that I use. But I guess in the general public, it's not such a commonly used phrase. And so Merriam-Webster states that the first known use of dark matter was in 1979. So it's not too recent, but also not too long ago. However, this is not entirely correct. Because Fritz Zwicky, who's a Swiss scientist, actually first wrote about something he called Dunkelmaterie, which is German for dark matter, in the 30s. But so I guess Merriam-Webster is counting the first English use of dark matter. So that was in the late 70s. But Fritz Zwicky was already thinking about dark matter back in the 30s. Okay, so here's the kind of the dictionary definition for what dark matter is. So next question that you are probably asking yourself is, okay, you've explained what dark matter is, but why do we think it exists? You made this claim that we think it exists. What is that evidence that it exists? And I like this. So this is not a cartoon from Mary. This cartoon I got from Greg Kogan's website here. I thought it was a bit funny. It's not, I don't think this is actually how astronomers are working. But the caption says, "That isn't dark matter, sir. You just forgot to take off the lens cap." Cue. Laughter. Okay, so let's say we take off the lens cap and we start observing the universe. So why do we think that dark matter exists? So I'm going to go through several arguments for the evidence for dark matter. And in particular, I'm going to go through the evidence at various scales, so different sizes of observations, and demonstrate why at each scale we think that there is dark matter. So the first evidence for dark matter was looking at the size, something the size of a single galaxy. So for example, the Milky Way, or in this case, looking at the galaxy of M33. That's the figure that I'm showing here. And so when you look at a galaxy, you can measure the speed that the stars within the galaxy, like so the luminous stars, are spinning around in the galaxy. And this is what's called the rotational velocity of the stars. And the speed of those stars is determined by the amount of mass that it's orbiting around. So this is something that you learn if you take freshman mechanics in college, is how to calculate how fast an object would be going based on how much speed, how much mass it's circling. So I'm showing here a figure which is showing on the vertical axis the velocity of these stars versus the distance the stars are away from the center of the galaxy. And so based on this kind of these equations that we know that tell us how fast a star is going to be moving based on how much mass it's circling and how far away it is from the center of whatever it's circling, you would expect this dashed line. So the dashed line is if the amount of mass that these stars are circling is only what we can see, what we call the visible disk. So that's the prediction if the only matter in this galaxy was from the visible stars. However, you can make observations. So in the yellow, it's observations from starlight. And in blue, it's a different type of observation from what we call 21 centimeter hydrogen. It's a different type of measurement that astronomers can make. And this measures the speed of the stars. And they see that it actually tracks this solid white line. So you see, especially as we start getting farther away, so as you start going to the right of this plot, these two, the dashed line and the solid line, really start to diverge. They really start to differ from each other. And the observations match with the solid line. So what this is telling us is that the amount of mass that these stars are orbiting is actually much more than what we can see, what we're observing. And if you plug in some what we would call dark matter, if you plug in this extra form of mass, you can recreate these the solid curve, and that matches the observations. So this was kind of one of the first evidences for dark matter, and kind of the pioneering work looking at these galactic rotation curves happened in the 70s with Vera Rubin, whose photo I've put on the slide, and her collaborator Kent Ford in the 70s. So they first looked at Andromeda and made this measurement and saw that, hey, the observations don't match with the prediction with this dashed line. And then they looked at many, many other galaxies and kept seeing the same behavior. So it's not just an off chance that Andromeda didn't have had this odd behavior, but all the galaxies that they looked at had the same behavior. And this is a similar kind of observation that Fritz Zwicky, the Swiss scientist I mentioned earlier, made, but he was looking at clusters of galaxies. But it was a similar thing that the behavior of these galaxies didn't quite match up with what you would have predicted. And so you needed to add in some extra mass into the system. And so that's what we call dark matter. And speaking of Vera Rubin, there was a new telescope called LSST, or it's not new, it's an upcoming telescope named LSST, but it recently was renamed the Vera Rubin Observatory in honor of Vera Rubin, who unfortunately passed away, I believe last year, fairly recently. So she has this legacy of in astronomy now. Okay, so this was the evidence for dark matter at the scale of a single galaxy. Now we can move up in size, which is to look at, let's say, two galaxies. And I'm showing here a photo of, it's a very famous photo, it's of the Bullet Cluster. So this is a snapshot of two galaxies that collided and passed through each other. And this is a really impressive photo because it provides really clear evidence that there's two different types of matter. So baryons, so the stuff that makes up everything that we know, and dark matter. So you might be asking, how do we see that with through this photo? And so I want you to keep in mind here that there's two different colors in this picture. There's the kind of the pinkish red color and the bluish color. So this is kind of it's not actually pink and red, but it's how we can visualize what's going on here. So what's going on here? On the left-hand side is a contour map of kind of where the mass is in this system based on something called gravitational lensing. So this is the idea that if you have something massive, it'll bend light around it. So it makes like a lens around it. And so you can do this exercise of looking at gravitational lensing, and you can see where all the mass is in this system by looking at the stars behind it. And they have to pass through the gravitational potential. And what you get is that there's two kind of like more dense collections of matter. So that's the two dots kind of on the left and right of the picture. So I'm still in the left-hand picture here. And then it slowly diffuses out. On the right-hand side is an X-ray image of the gas that's in this in the bullet cluster. And you can see that the concentration of gas, so the brighter the color, so the yellow is where there's the highest concentration and blue is more diffuse. The highest concentration of gas is kind of in the middle, so not quite lined up with the circles of the green plot. So what this is telling us is that the gas is mostly concentrated in the middle, but the majority of the mass in the bullet cluster is offset, is off to the side. And so this is another evidence that there's dark matter. And we learn an additional thing about dark matter is that it doesn't interact very much with itself, with each other. So the reason why the gas, this yellow and red blobs are kind of in the center is they interact with each other. So you can think of this as being like, if you go to a party and you have two groups of people who are coming together, the really social folks are going to stop and chat with each other and like, oh, hey, how are you? It's been a long time no see. And the antisocial folks are just going to keep walking. And so they'll get farther apart from each other. So in this picture, we can think of the gas, baryonic matter, as being very social. They're kind of like the social butterflies, and they want to catch up with each other. They interact a lot with each other. And so they kind of stay in the middle. Whereas dark matter is much more antisocial. It doesn't want to interact with its fellow dark matter companions. And so it keeps going in the direction that they were traveling. Okay. So this is the evidence for dark matter at the size of a couple of galaxies. And there's the bullet cluster is not the only one that has this behavior. So you can look at other galaxy mergers and you would see similar behavior. Just the bullet cluster is kind of one of the most famous examples of this. We can now move on even larger in size, which is looking at clusters of galaxies. So many galaxies. So the previous slide was looking at 2 galaxies. Now I'm talking about billions of galaxies. And there's evidence for dark matter here by looking at how these galaxies clump up together. So here's a kind of a graphic I took from this paper by Springle, Frank, and White from 2006 that's showing you, so all the bright stuff, so blue and the yellow, are galaxies. And it's showing you how the galaxies would look in our universe given a certain model. So in the blue region, this is the model for a universe that has a specific amount of dark matter. So in particular, the amount of dark matter that we believe is in our universe. And you would see that the galaxies clump and make filaments in a very specific size. And then you can actually look at our universe. You can point your telescope at the sky. And this is what the Sloan Digital Sky Survey did. So they pointed the telescope at the sky and they mapped out where all the galaxies were in their visible, what they could see. And they got what's in the yellow. And so if you do a more sophisticated analysis, a more quantitative analysis, you find that these are very consistent with each other. And in particular, if you didn't have dark matter, you wouldn't be able to form the same kind of structures that we observe. Okay, so these dark matter is really what causes the galaxies to cluster. And the fact that these galaxies clusters then also means that you can start forming more and more stars. So stars are born in these galaxy clusters. And so I heard a colleague once say, we can all think of dark matter as being our mother. If it weren't for dark matter, these galaxies wouldn't have clustered in this way. And we wouldn't have formed stars and we wouldn't have made everything that we know. So we can thank our existence to dark matter. Okay, so that was the evidence for dark matter at the size of many galaxies. So now let's look at something that's on the size of the universe, of our observable universe. So this one is it's a little bit more technical, but I hope it provides some sense that really over many different size scales, we have pretty strong evidence for dark matter. So the last evidence I wanted to talk about is from what we call the cosmic microwave background. or the CMB. So this is often abbreviated CMB. And this cosmic microwave background is the furthest back in time we can see using light, right? Because light has a certain speed limit. That's the speed limit of the universe. And it can travel a certain distance in the lifetime of the universe. But anything past that distance, we can't see. So you can think of this as being like a baby photo of our universe. It's when the universe was about, I think, 300,000 years old after the Big Bang. And imprinted on this CMB in this photo are hot and cold spots. So these are the blue and red patches on this that kind of tell you where matter starts to clump up, and are then the seeds for which the stars and galaxies that we know eventually are formed. On this, the bigger plot I have in this slide kind of shows you 3 different experiments or 3 different telescopes that were looking at the CMB. So the first baby photo of the CMB was taken in the 90s from a satellite called the Kobe satellite. And it had okay resolution, so you could start to see the red and blue spots. But it would be like if you looked at the Earth on the right-hand side, and you can start to make out the shapes of the continents, but it's pretty blurry, right? You still can't really see any of the details. 10 years later, we have the WMAP satellite, which had much better resolution. So the equivalent, kind of the analog, would be if you looked at the Earth, and now you can start to see like the Sahara Desert, you can see Greenland, you can start to make out the shapes of the mountain ranges, but not quite. So this was WMAP, and so you start to see smaller features in this red and blue patches. And then more recently, we have the Planck satellite in 2013, and they recently released newer results last year, where it's the most exquisite resolution that we have so far. And you can, if you were to look at the analog on the Earth, you can really start to see the fine features of what's happening on the Earth. And so that's the kind of resolution that we now have with Planck. You can really start to see where these different patches of hot and cold photons, so it's the different energies of the photons, are sitting, which therefore tell you where stars and galaxies are going to form. So with this picture in mind, we can look at, there's a measurement you can make that tells you where the red and blue spots are relative to each other. So it gets fairly technical, but the point I want to make here is that you can make this measurement, and it'll give you a curve that looks like what I'm showing here on the slide, a curve that has these peaks and then these troughs. And the size of the peaks, as well as the ratio of the size of the peaks, one tells us about how much matter and energy is in the universe, as well as how much dark matter and baryonic matter there is in the universe. So the very first peak, the tall one, tells us about how much energy density is how much stuff is in the universe. Whereas the second, the ratio between the first and second peaks tells us how much baryonic or normal matter there is. So the key thing to take away from this plot is the relative heights of these various peaks. So you might ask, okay, how do we get dark matter from this? And to see that, I wanted to show a little cartoon GIF. It's not a cartoon, it's actually a calculation that this professor at University of Chicago, Wayne Hu, made, which it's the same peaks and troughs that we saw before. And on the right-hand side, you'll see this little magenta bar. And the height of the magenta bar tells me how much dark matter I've put into my universe, into my simulation. So the higher the bar is, the more dark matter I have in my universe, and the lower the bar is, the less dark matter I have. And so what I want you to pay attention to is how the heights of the yellow peaks change as I increase or decrease the amount of dark matter in the universe. So you see that as I increase the amount of dark matter, the first peak starts to come down, and in particular, it starts to become similar to the height of the second peak, and the third peak becomes higher. And as I decrease the amount of dark matter, the first peak becomes very high, and then the second peak and the third peak become lower. Right, so this, as I change the fraction of dark matter that I have in my universe, I can change the shape of this plot. Okay, so we can watch it a few more times. So I'm increasing my dark matter, decreasing my dark matter. Now I'm increasing the dark matter again, and then decreasing the dark matter. Okay, so this is a prediction. So given a certain amount of dark matter, this calculation will predict what the yellow curve will look like. But what's great is with these satellites, in particular with Planck, we can measure what that yellow curve is. And in this case, now it's blue, but it's the same curve. It's the same measurement. And the red dots are the actual data from the Planck satellite. And the blue line is the model for a specific amount of dark matter. So in this case, 80% of matter. We've put 80% of matter as dark matter. And you get this blue curve, and you see that it really sits beautifully on these red dots. It matches all the peaks, especially at the right side of the plot. The error bars are so small that you can't even see them. And I would say this is probably the strongest evidence that we have for dark matter, in particular that dark matter is some new particle. I would say it's from the CMB. So the CMB is this really exquisite measurement we have of the cosmic microwave background of the early universe, of how photons were distributed in the early universe, which then tells us how stars and galaxies are going to form. And it requires a certain amount of dark matter to match what we measure from the Planck satellite. Okay. So to summarize a bit, I've provided some evidence that we have for dark matter across 4 different scales. So the first one I talked about was at the galaxy scale, the size of a single galaxy. And this was looking at the galactic rotation curves. Next, we looked at galaxy mergers, so the size of two or a few galaxies. And we also saw that there was this very strong evidence for dark matter. We can go up in size and look at galaxy clustering to see how the matter in our universe kind of distributes itself around the universe. And that also required dark matter to get what we observed. And finally, I talked about the CMB, which kind of is this baby photo of the universe. And we saw that we also needed to include dark matter to match what we measured out from these satellites. So one thing that you'll note, or I hope you know, otherwise I'll tell you, is that all of this evidence that we have for dark matter on all of these scales is purely gravitational. It's just telling us how matter moves interacts with gravity. And so the fact that it's all gravitational means we know that dark matter has a mass. Mass interacts gravitationally. That's the force that mediates between two massive objects. So all of this evidence is gravitational evidence. So if you think way back to the slide I had of the Merriam-Webster dictionary definition, it says that we know of dark matter through various astrophysical measurements that are based on its interactions with gravity. So here is the evidence that we use. Okay, so I've given you this whole spiel about why we believe dark matter exists. And so here on the left-hand side kind of gives you a scale of how dark matter fits into the bigger scheme of things. So on the left-hand side, the black pie chart shows you the energy budget of the universe. So this was also one of the trivia questions. And we see that ordinary matter makes up about 5% of our universe, whereas dark matter makes up 25% of the energy matter budget, what we call the energy matter budget of the universe. And the rest of it, 70% of it, is what we call dark energy. So I'm not going to talk about dark energy at all in this talk. It's a completely separate topic that reserves its own science pub for sure. But in short, dark energy is what's causing our universe to expand and to accelerate in its expansion, and this got the Nobel Prize several years ago. Okay, so let's zoom into this ordinary matter slice, this 5%. So we can zoom in here, and then we get the second pie chart on the right-hand side. And this tells us how ordinary matter is distributed throughout our universe. And so you see most of it's gas. So in the trivia question, it was talking about matter in our galaxy. So within our galaxy, the most matter is in dark matter, and the next greatest proportion of matter was in stars. But if you look at the whole universe, actually most of the matter in our whole universe is in gas, in intergalactic gas, so not even within the galaxies, it's just in between the galaxies. And the stars in the galaxies are 7% of ordinary matter. So take 7% of 5%, and you'll find that stars, everything that we know that basically makes up everything that we know, and that's us, is less than 1% of the matter in the, or of like less than 1% of what makes up the universe. So 25% of this is that dark matter. So it's such a big number of what makes up our universe. So that gets back to our original question, is what is dark matter? So I've given you all this evidence for what dark matter is, but we still don't know what it is. So the hypothesis, kind of the leading hypothesis within the field, is that maybe it's a new particle. So I'm a particle physicist. I know how to think about particles and their interactions with other particles. So maybe dark matter is a new particle. And in particular, because dark matter interacts gravitationally, it needs to have a mass. So maybe it's a new massive particle. So let's start with that hypothesis, that dark matter is a massive particle. Okay, so what kind of mass can it be? Well, it turns out there's a huge range of masses that dark matter can be. So it can go from, so the electron volt is a unit that we use in particle physics for mass, also for energy. For us, it's you can interchange between the two. And this range of masses that dark matter can have is 36 orders of magnitude. So this is for a particle dark matter. And so at the lowest end, we have 10 to the minus 22 electron volts. So if you're not familiar with the size of that, that's very, very light, very, very small. The electron is about 500 keV, so that's 500,000 electron volts. And the proton is about 1 billion electron volts. So they kind of sit on this plot in this way. And on the high end, it's about 1,000 uranium atoms. And a uranium atom is about 200 billion electron volts. So there's a huge range of masses that this particle dark matter can take, which seems a bit overwhelming. Yeah, where do you start? Well, there's been one region in this kind of mass range that has been very popular and has been the main focus of much of the dark matter research. And this is dark matter that's between the size of, say, about a proton to about 1,000 uranium atoms. And in this category of dark matter lives a candidate called the WIMP. So it stands for Weakly Interacting Massive Particle. And if you follow science and astronomy or particle physics at all, you'll realize that scientists really, really love acronyms. So the WIMP is an acronym for Weakly Interacting Massive Particle. And in short, the name is somewhat descriptive. It's a massive particle that interacts, at least the first iteration of it was that interacts via the weak force. So this is what the W and Z bosons that I showed in the first slide, that's the force that they mediate. Turns out that version was ruled out a long time ago, but that was the first iteration of this WIMP. And WIMPs are roughly kind of on average 100 protons in mass. So given that that size of WIMPs, there's about 10 million that pass through your hand each second. And so we saw in the trivia that was like about 100 million that pass through your body at each second. So why was the WIMP so popular? Why was all this effort being spent looking for the WIMP? Well, it was very popular for something that we called the WIMP miracle. Okay? What was the WIMP miracle? The WIMP miracle was this kind of numerical miracle where if you have a, let's say, 100 GeV dark matter and it interacted via the weak force, if you went through the evolution of this dark matter, you would get exactly the amount of dark matter that we observe now in the universe without having to really fiddle around with the numbers very much. So given this kind of vanilla WIMP model, you got exactly what is observed. The prediction from that matches the observation of dark matter. And so scientists would say, there's no such things as miracles. There must be a reason for this coincidence of numbers. The WIMP is a very well-motivated candidate. So a lot of both the theoretical and experimental work in the last several decades has been focused on this WIMP. So here's another slide from Mary's comic. There's a lot of text here, but it's basically giving you a short summary of the WIMP. So it was invented or first proposed in the 80s. So it has this like 80s vibe to this comic. And I explain here about the WIMP miracle. The other thing that made it theoretically like very appealing was that there's another theory unrelated to dark matter called supersymmetry that particle physicists have studied for a long time. And the WIMP naturally falls out of, like, it occurs in models of supersymmetry. So in these models that were completely unrelated to dark matter, you have a particle that you predict that happens to match all the characteristics of dark matter. So that was really nice. So I've explained why what dark matter could be and why the WIMPs were kind of the most popular candidate, and in fact have been driving the paradigm for dark matter for quite some time, for several decades now. Okay, so now that I have this hypothesis that dark matter is a WIMP, you can ask, how do we look for WIMPs? So I'm a scientist, I have a hypothesis, I need to test it. So you can look for WIMPs in several different ways. So you can look, so here's another page from Mary's comic. So you can look for them using large underground detectors, using accelerators or colliders, such as the Large Hadron Collider at CERN in Switzerland, or at telescopes. So the telescopes is a lot of what I've already been discussing. But I want to focus on this first topic of looking for the dark matter, the WIMP, via large underground detectors. So the idea here is, so this is a technique which we call dark matter direct detection. The reason why it's called direct detection is because you're looking for the interaction of dark matter with us. The idea here is I have some target, so my detector, which I've drawn in blue here, made out of some material. Okay, and all materials that we know about are made out of atoms, which are a nucleus and an electron, or nucleus and many electrons. The idea with dark matter direct detection is you have dark matter. So we're surrounded by dark matter, as we learned in the trivia. We have this dark matter halo in our Milky Way. And so there's constantly dark matter passing through the Earth, passing through us. And the hope is that every once in a while, one of these dark matter particles is going to interact with the atoms of your detector. And it's going to hit the nucleus of the detector and make it jiggle. And so what you look for is this jiggle, what we call the recoil of the nucleus. So this is a very small signal. And you can see there's a lot of other things in the world that can or in the universe that can cause this nucleus to move. For example, cosmic rays, stuff coming from the atmosphere, other particles coming from the atmosphere. So because it's a very sensitive process with a lot of other processes that can mimic this signal, typically you put these detectors, some are very deep underground. And this way you can use the Earth as a shield, right? Because cosmic rays interact a lot with other matter. So it's going to interact a lot with the Earth and it won't ever reach the detector underground. Whereas dark matter doesn't interact very much. Remember, it's fairly antisocial. So it'll make it down to your detector. Okay, so if you put your detector somewhere very deep underground, you can shield the detector from things like cosmic rays, and this is what we call backgrounds. Cosmic rays are a background. So the dark matter is the signal, and everything else is a background. It's kind of extra, what we're not interested in. Okay. So this has been the technique with dark matter direct detection, is to have some detector and you put it very deep underground. And currently, the largest of these detectors that if you are interested in dark matter, you may have heard of in the news fairly recently, is an experiment called Xenon 1 ton. So here's a photo of Xenon 1 ton. On the left-hand side of this picture is a big tank. And this tank is filled with liquid xenon. And how big is this tank? Well, you can get the size of this tank looking at the right-hand side of the photo, which are the offices and the laboratories at this lab. And this is a 3-story tall structure on the right-hand side. So we have like a 3-story tall tank of liquid xenon. So it's about one ton of xenon, hence the name, looking for dark matter. And this Xenon 1 ton detector is in Italy. It's at the Gran Sasso National Laboratory. So I have a little photo of Italy here. And you can see with a dot where on the boot Gran Sasso lives. And Gran Sasso is kind of a mountain range. And the laboratory that Xenon 1 ton is sitting in is about 1.4 kilometers underneath all the rock of Gran Sasso. So it's really being shielded and protected from cosmic rays by the mountain and the Earth on top of the laboratory. So currently, this is the largest direct detection experiment. So you may ask, why xenon? Why liquid xenon? And the reason why liquid xenon is really good for looking for WIMPs is in the atomic mass of xenon, so the size of a xenon atom. So a xenon atom is about 131 protons in size. And remember the WIMP, the vanilla WIMP was about 100 protons in size. And this idea with direct detection is you're hitting two things against each other and you're looking for the movement of one of them. So if these two things are comparable in size, you get really nice energy transfer and you get a large recoil, a large jiggle of your nucleus. So the reason why xenon has been really great for looking for WIMPs is it's comparable in size to the canonical, the idealized WIMP, or the vanilla WIMP candidate. And now we have 1 ton of this liquid xenon. It's a lot of target material. And this has been going on for several decades with really exquisite precision. So xenon is ideal for WIMPs, but so far, no signs of a WIMP, no signs of WIMP dark matter. So this then, for some folks, in particular for me, caused me to start to think, what if dark matter is not a WIMP? So what if all this effort looking for dark matter as a WIMP was looking for dark matter that didn't exist? What if dark matter is actually some other mass range? And in particular, so let me go back to this slide that shows you the range of masses that dark matter can have. So from very, very light on the left-hand side to fairly heavy on the right-hand side. And the green is where the WIMP lives. And I've been interested in the last several years in dark matter that lives in this region in between the size of an electron and a proton. The question is, what if dark matter lives here? Right, this is actually my favorite kind of dark matter candidate. It lives here. Turns out if dark matter lives here, so if it's lighter than a proton but heavier than an electron, this is a problem for xenon. It's a problem for direct detection experiments that use xenon or argon, etc. The reason why this is a problem, so remember the idea with direct detection is I have my dark matter, it comes in, it hits the nucleus of the xenon, and it transfers some energy to the nucleus, and the nucleus jiggles. However, the dark matter is really small. If it's 1% of the size of the nucleus, the amount of energy it can transfer to the nucleus is tiny. And this jiggle that the nucleus makes is very, very small. So you can think of this, for example, as like if I have a bowling ball, the nucleus is a bowling ball, and my dark matter was a ping pong ball. And I threw my ping pong ball at the bowling ball is not really going to move. If it was 2 bowling balls, yeah, I could make the other bowling ball move. But if the dark matter were the size of a ping pong ball, it's not going to be able to make the bowling ball move at all. So this jiggle is really small. And therefore experiments like xenon, which are looking for this nuclear jiggle, are not going to be sensitive to this the sub-GeV, sub-proton mass dark matter. So that might sound terrible. What do we do? Well, you do make the observation, the way that you get around it is that, okay, all atoms, not only do they have a nucleus, but they have electrons. And electrons are much lighter than the nucleus. In fact, they're less than half a proton, actually much, much smaller than a proton in mass. And so if I have a dark matter that's more comparable in size to an electron, I can look for it hitting the electron instead of the nucleus. And I would look for the electron signal instead. Okay, so this was an idea that some collaborators and I had, and we worked through the calculation. And it turned out to be actually a very promising way to look for this class of dark matter candidates, what we call sub-GeV dark matter candidates, so below a proton mass in size. And this led to the formation of a collaboration called SENSEI. So SENSEI is an experiment, a dark matter experiment that's currently based at Fermilab, and it's in the process of moving, and funded by the Heising-Simons Foundation. And this is an old photo from 2018, from a couple of years ago, of the SENSEI experiment. So SENSEI itself is also an acronym. Like I explained, physicists love acronyms. So SENSEI, okay, it means Japanese, teacher in Japanese, but nobody on the collaboration is Japanese. But hopefully we can learn something about dark matter with it. I guess that was it was an aspirational name, but it's also an acronym. And so what does SENSEI stand for? It stands for Sub-Electron Noise Skipper CCD Experimental Instrument. That's kind of a mouthful. It tells you a bit about what the instrument is like. But what I always find really funny about this acronym is that I would say the most important part of it is CCD. Like that's the material that we use for the detector, but it's not part of the acronym. So we skip over that CCD part. And the rest of it kind of tells you we use a special technology called skipper technology, and we're able to make really precise measurements that are below an electron in size. And so it's a quite small experiment. So remember the xenon 1 ton experiment was this 3-story vat of liquid xenon. So Sensei is, at least this iteration of Sensei is sitting inside this copper, so I have this arrow on my slide, inside this copper tube, which you can see is, you know, about 1.5 feet tall and like a few 8 inches, around maybe 10 inches around in diameter. So pretty small, much smaller instrument than the xenon experiments. So here's some nice photos, some close-ups of Sensei. So the actual experiment is in the left photo is that gray rectangle. So we surround it by copper because remember the reason we want to put these detectors deep underground is to shield it. But the Earth is not quite enough, so you also have to cover it with copper and then cover that with lead. So even though the detector itself is small, it looks much bigger because you have all this shielding around it. So what's great about Sensei? Well, Sensei was the first dedicated detector looking for this class of dark matter that's lighter than a proton, what we call sub-GeV dark matter. More recently, now there's other experiments that are looking for this class of dark matter, but Sensei was the first one to really be built for this purpose. And really recently, we got this nice recognition for this work. So this is the New Horizons and Physics Prize that's given out by the Breakthrough Foundation. And so they gave me, so I'm down there at the bottom of this red box, me and 3 of my collaborators, so Ruben Essig, who's at Stony Brook University, Javier Tiffenberg, who's at Fermilab, and Tomer Volansky, who's at Tel Aviv University. They gave us this really nice recognition for the work that we've done to look for sub-GeV dark matter, and especially in the creation of the Sensei experiment. So this happened a month ago, 2 months ago, this award. So it's nice to see this work that we've been working on for several years, getting people excited, which is fantastic. So I said that Sensei was a silicon. It's a CCD, and I said that CCD I thought was the most important part of the name, even though it wasn't in the acronym. So you might be asking, what is a CCD? So CCD is yet another acronym. It stands for Charge Coupled Device, CCD, Charge Coupled Device. And the invention of the CCD got these 2 gentlemen on the slide, Willard Boyle and George Smith, the 2009 Nobel Prize. So you might be familiar with CCDs because they're commonly used in digital cameras. So here's in the middle of my slide, I have this photo that I grabbed off the internet of a CCD chip from a Hewlett-Packard digital camera. On the left-hand side is another CCD camera, like a surveillance camera. And on the right-hand side is a photo of the Sloan Digital Sky Survey. So this might sound familiar. This was the sky survey that made that galaxy clustering map that I showed earlier in the talk, the one with the yellow part of it. So the Sloan Digital Sky Survey was measuring kind of galaxy clusterings using CCD chips as the camera type. So it's widely used in digital imaging. And the idea with the CCD is that it converts photons into some digital image. This is why it's used in cameras. But the basic idea with Sensei is that instead of looking for photons, you would look for dark matter. So you're basically taking a photo of dark matter using your silicon CCD. So here's like a zoom in. So on the top right, I have a cartoon of an array of pixels of my CCD. Then zoom into 1 pixel, and I zoom in even more into that pixel, and you see I have a dark matter that comes in. It hits one of the electrons that lives inside the pixel, and it bumps that electron out, and you look for that electron that got hit. And so this is how we look for dark matter using Sensei, using silicon CCDs. Okay, so we're currently taking data at Fermilab, but the future of Sensei is that we're actually currently moving the experiment to SNOLAB in Canada. So here's a Google map shot I took. So Sensei is currently living in Fermilab, which is a national laboratory in Batavia, Illinois, right outside of Chicago. But the goal is to get Sensei to Canada and to SNOLAB. So you might ask, why do you want to move to SNOLAB? Well, remember I said it was really important for these direct detection experiments to be deep underground. And at Fermilab, we can only get 100 meters underground. That was the facility that's there. And at Snow Lab, we can go about 2 kilometers underground. So it's a much more quiet environment, a much larger shield. And we're in the works of making it slightly larger, so 10 grams of silicon at Snow Lab. So this is going on. We'll hopefully start taking data with this, the Sensei at Snow Lab at the beginning of next year, so around January. But in the meantime, I recommend you stay tuned. So perhaps you'll hear about Sensei in the news. Thank you.
All right, thank you very much. That was that. I hope I didn't cut you off, but it sounded like you were wrapping up. Okay. Well, that was fascinating. A little bit over my head, though. There were a couple of parts where I was like, I'm going to have to ask some questions here.
Good.
So we've been, and just for everyone who's watching, if you missed some of the first parts of the discussion, or when we first opened, if you have questions for Dr. Yu, please feel free to send them to us on Facebook. You can drop them in the comments of this video that we're streaming right now. And then I will get those questions and I will ask them to Dr. Yu for you. So just to get started, how, and this is a little general, but how did you get interested in studying dark matter?
I don't know. I find it's okay. I think it's kind of a natural like humans are curious, like we're a curious species.
Sure.
And I think for a lot of people, we want to know kind of how the universe works, what makes up everything around us. So it's kind of a continuation of that line of thought is, oh, actually most of the universe, we don't know what it is. And at least a slightly more tractable part is dark matter. Okay, there's also dark energy, which I think is also very interesting, slightly harder problem to tackle. So dark matter seemed like a big problem unknown, but at least there were some clear directions to try to pursue.
And then for you,
and I got started getting into, yeah, go ahead.
Oh, I was just gonna ask, I mean, for you,
I got started with physics, being interested in astrophysics, so.
Okay, so it was kind of like an astrophysics thing, galaxies, the stars, all this stuff, and then it kind of led you down that path?
Yeah, and I eventually, when I went to grad school, I ended up studying particle physics and not astrophysics. But and so dark matter is this kind of beautiful marriage of both particle physics and astrophysics. So I get to do both.
Wow.
Dark matter.
What would you say, and this is just kind of a dovetail off of this, what would you say are some of the biggest misconceptions or misunderstandings about dark matter that you encounter?
I guess there's yeah, that's a good question. I guess I haven't talked to too many folks who have too many misconceptions. I guess one that always comes up is, why do you think dark matter exists? Maybe we just don't understand gravity, because a lot of the evidence that I showed earlier was all gravitational. The big question is maybe we just don't understand how gravity works. And that's a really interesting question. I think it's a perfectly fair thing to ask. In fact, that's probably one of the first things you should ask, is maybe we just don't understand gravity. But if you really go through and start to look at the various measurements, you see that just modifying gravity doesn't quite work, especially for the CMB measurement. It's really hard to make it compatible with that measurement. So I do think you could modify gravity. So I guess the big misconception, I say, is that dark matter doesn't exist. And I think it does exist because we have this evidence across all scales that it exists. And okay, maybe modifying gravity works for some of those cases, but it doesn't work for all of them. Whereas having a new particle that we call dark matter does work, does explain all of that phenomena. Another one that sometimes comes up is, can you harness dark matter to be some new energy source? And that's difficult because dark matter doesn't really interact with us, so it's hard to make it do anything that we want it to do.
Yeah, that's really interesting. So, and you may have touched on this, and I may have just totally gone right over my head, but it's dark matter, and there's, at this point, there's no way for us to actually, with instruments or anything like that, actually physically see it, right? Like we could see different spectrums of infrared and that sort of thing, but we can't like see dark matter. And I'm just asking this as a clarification, so that way I'm totally on track.
Yeah, so dark matter doesn't, the only way it interacts with light is that it can bend light. So in that way, that sense it does interact with light, but it doesn't reflect light. You don't see it in the normal way that we think about seeing things. I would say like this gravitational lensing, which is the fact that dark matter or anything massive can bend light. In some sense, that's a way to see dark matter. So I didn't have a photo of this, but there's these really, if people are interested, you can look up things called Einstein rings, which are these images of stars and galaxies. So you have stars and galaxies, and then you put like a dark matter blob in front of it, and then so the blob is between you and the stars. And because the light has to bend around, if it has to bend a lot, it actually starts forming rings around the lens. And there's these photos that have been taken with telescopes where you can actually see these arcs of the background galaxy getting bent around.
Oh, fascinating.
So you don't see the dark matter, but you see the effect of it in a very visible way.
Interesting.
I think that's pretty cool.
Huh? Kind of like wind.
Yeah, you see the effect, you feel the effect of it. In fact, there's an effect called the dark matter wind, which is the fact that we're traveling around our galaxy. So depending on the time of year, either there's a headwind of dark matter, so we're going into the dark matter, or we're going away from it.
Interesting.
This is one effect that's predicted about dark matter, this dark matter wind.
Interesting. All right. Okay. Well, let's move on to this next question. What do you hope to learn by studying dark matter? Are there practical applications, or is this are we just further understanding the universe? Where do we fall on that in terms of studying dark matter?
Yeah, that's a great question. I think I get asked that quite a lot actually, or I guess particle physicists oftentimes also get asked, what are the practical applications of what you do? And I would say, okay, I'll hedge a little bit on this question. I think it's important to study fundamental science, for example, what dark matter is because it really taps into, like I was saying, this curiosity that we have as humans. And I think that's the thing that kind of keeps us going, that keeps us kind of moving forward, even if things seem really dire. It's something much bigger than us. It's much bigger than our society. It's much bigger than our world. And kind of, I don't know, in some sense, put things into a certain type of perspective. And I know you get this feeling of wonder of what is dark matter, and it kind of reminds me of being a kid again and be like, oh, what is everything? So it's getting to experience that every day as my job. It's pretty awesome. Okay,
cool. Yeah. Hey, we're all about getting curiosity going over here. So we're in the right ballpark. Okay. Here's one. Oh, we touched on this a little bit. Is dark matter affected by gravity, or does it only generate gravity? If it's affected, could it collapse into a black hole?
That's also a really great question. It's a bit of both. So gravity is the force that kind of exists between massive objects. So dark matter, even us, we kind of provide a gravitational field because we all have mass. So in particular, I'm actually gravitationally attracting this laptop towards me, but it's such a small effect that I'm never going to notice that the laptop is feeling like it's pulled towards me. It's also being pulled to whatever is behind it as well. So in that sense, dark matter affects, like it generates gravity because it has a mass. But because it has a mass, it also feels the gravitational effects of everything else. And this is part of the reason why, like, you can have, this is why you needed dark matter to form galaxy clusters, because the dark matter was kind of pulling ordinary matter closer towards it through that gravitational interaction. And that's right, you could try to pack a lot of dark matter in one spot, and if you could make it dense enough, it would eventually collapse, like a star would into a black hole. But it's you would need a very high density of dark matter, which could be tricky to do. But on the other hand, okay, maybe a follow-up to that is, so the Nobel Prize this year was half to Andrea Ghez and Richard Getzel looked for the discovery of Sagittarius A star, which is a supermassive black hole in the center of our galaxy. But we also expect that the highest concentration of dark matter in our galaxy is around this black hole, because the gravitational pull of it is so strong that most of the dark matter, or a lot of the dark matter, maybe not most, a lot of the dark matter is also going to be in the center of the galaxy. So often we point telescopes at the center of the galaxy, also in hopes to see some indirect signature of this dark matter.
Okay. Very interesting. Okay, let's see. How does dark energy play into this model, considering it's 70% of the universe? Thanks from a fellow, okay. I'm guessing that's a badger. Wolverine.
Ah, yeah, Wisconsin is a badger.
Oh, okay. Thanks from a fellow badger. Got it.
Yeah. I hope it's a badger. Yeah, I'm a former badger. Yeah, so dark energy is, I went over this very, very quickly, but dark energy is what we call whatever thing it is that's making our universe expand. So our universe is expanding. This observation was given a Nobel Prize, I think it was in 2011. I'm a little fuzzy on my dates. And the fact that not only is the universe is expanding, but it's accelerating as it's expanding. So it's like this negative energy density. It's whatever's pushing the universe out. And that's what we call dark energy. We don't really, this is also a huge question in physics. What is this dark energy? And it fits into, you could kind of see hints of it in the plot I showed of the CMB, of like these peaks and troughs. The size of that first peak kind of told us how much dark energy there was. You can think of it that way. But beyond that, there's not necessarily a priori any connection between dark energy and dark matter. There doesn't have to be. You could write down a model where they are related, but they don't have to be related.
Okay. All right. I don't know how to. All right. I've heard that the nightmare scenario is that dark matter may only interact with gravity and therefore may not be testable. What is your opinion on that?
Yeah, I think that's a very valid thing to wonder, because the only evidence we have of dark matter is gravitational. So you could say, why do you expect it to interact any other way? So especially in this direct detection picture, the first assumption you have to make is that there's some interaction beyond gravity that the dark matter has with our normal matter. And yeah, it is an assumption, but I think it's a fair assumption to make, because dark matter was produced at the early universe with everything else. So it might interact very weakly with everything else, but there's no reason why it would be completely isolated from normal matter. So that's one way. But okay, let's suppose that it only interacts gravitationally. There are some proposals for various experiments you can do that also look for these gravitational effects that would be able to test at least certain classes of dark matter. And people have been working on this because, yeah, that's a natural question to ask, is what if that base assumption that it interacts beyond gravity is false? Are we doomed? Is it nightmare? So I don't want to say it's completely a nightmare scenario. Like, physicists can be very creative. We always find a way out of things.
Okay, nice. Oh, clarification. Did you say Einstein rings? Like yes. Albert Einstein?
Yeah, like Albert Einstein.
Okay, Einstein rings. So I think probably the clarifying question is, if I wanted to Google what you're talking about, I would Google Einstein, like Albert Einstein rings, to see this lensing effect of light.
You could also look up strong gravitational lensing. So that's where
gravitational lensing. Okay.
Yeah, that's what you would. That gives you that effect.
Do you know why it was called an Einstein ring?
I guess because Einstein worked on GR, and he was the first one to propose that space-time is you can bend space-time with gravity. Yeah. So that's what's happening. You're bending space-time, and the light is traveling on this bent space.
Okay. Interesting. Okay. So this next question is pretty good. So this could be probably a pretty dense subject or topic matter, I can imagine. So what sort of resources would you recommend for like grade school, middle schools, aged kids to learn more about this?
So I know for really small kids, there's like a series of like baby books, like, you know, these cardboard baby books that talk about, I think there's one about dark matter. There's definitely one about black holes. There might be one about dark matter. So this is for like very small, just learning how to read children. Other than that, like NASA has some really great websites. Like on their website, they have a lot of outreach, kind of more public outreach pages.
Yeah.
And for older, slightly older, like middle school, high school age, there's several magazines that I think do a really great job with science journalism for the public. So one is out of Fermilab and SLAC, so it's run by the national labs, and it's called Symmetry magazine.
Okay.
And there's another one that the Simons Foundation runs called Quanta. So this is actually sometimes it's a little bit higher level. So maybe a high school, college level would be able to follow it. Yeah, so I would say those are good places to start. Symmetry does a really great job in that a lot of times they have fairly interactive articles where you can like click through things, or they have quizzes. I think the journalists there do a nice job. I also mentioned these two because they're the two I'm most familiar with. I'm sure there's many others. And one of the hopes with the Science and Comics Fellowship that we started here was to actually have another way to kind of communicate this material in a way, not necessarily to kids, but just to anybody who is interested.
Yeah.
I feel like visual media is something that's very accessible to more folks than necessarily just written essays and text. So that was one of the goals with the Science and Comics Fellowship.
Cool. Now this is kind of another one of those how do we know type questions, but how do we know dark matter is not multiple different types of matter that we have not yet discovered?
That's a wonderful question. We don't know that it's not multiple different types of matter, and that's kind of a direction that the field has been going more in. And I would say the reason why you start off with this hypothesis that dark matter is one particle is because that's the simplest hypothesis you can have. And so in science, kind of how we work is you start with the simplest thing and you build on it. So you try to understand everything you can if dark matter was just one thing. And then you say maybe there's two particles that make up dark matter. Then what would things look like? And you just slowly add complexity. So there's no reason why it's only one type of matter. And in fact, I would be really surprised if it were, because ordinary matter we saw the standard model, right? It was many different types of particles, and that was 5% of the universe. So why would the other 25% of matter only be one species? It's not necessarily true. But I would say this assumption that it's one thing is kind of to make our lives simpler. So there's always this joke that physicists say, okay, assume a spherical cow. Okay, cows are not spherical, but that's what we know how to calculate. And then you can slowly start to make the cow look more cow-like. You can add a head, and then you can add some legs. And, but you first understand the spherical cow, and then you can make it more realistic.
Okay. Yeah, interesting. Okay. All right. Earlier in your presentation, you said when you say stay tuned to see if the electrons move, about how long should we stay tuned? Yeah, so Sensei itself has we've already had several results out with our two with our prototype and one with actually our science grade detector. And so our latest paper was earlier this year, so it's in PRL. But for the Snow Lab one, the hope is to get it up and running by January. And so within the year, we should have our first analysis of that data. Oh, cool.
But we're not the only experiment, right? There's many other experiments going on. So yeah, I would say these next several years are going to be pretty exciting for dark matter research, because there's so many different cool ideas that are being thrown out there. And then this looks like, at this point, no other questions are coming, but this is our last question right now. This was kind of a fun one, but what is your favorite and or perhaps most accurate reference to dark matter in pop culture? I think I'll have to go back to, so Symmetry magazine has a whole series of articles about dark matter. So not only just about general dark matter, but also about the various different candidates of dark matter. So they have one about, I didn't talk about them, but about axions, about primordial black holes, about WIMPs. So I'm just throwing out names of various dark matter candidates here. So the Symmetry magazine has quite a lot of a pretty extensive list of articles about dark matter.
Okay.
And yeah, so I would start there.
Well, all right. I think that's it for our questions. So, Dr. Yu, thank you very much. Okay.
Yeah, thank you for having me.
Yeah, wonderful. Well, that's it for tonight. I hope everyone enjoyed the event. If you'd like to watch it again or share with your friends, this video will remain on our Facebook page and on our YouTube channel. Don't forget to follow us on Facebook and Instagram and Twitter. We got all sorts of great stuff that we're talking about when it comes to other events and online presentations and things like that. I know I mentioned it at the beginning, but please consider supporting Science Pub and supporting OMSI with a donation. You can just do that right on our Facebook page. There's a big blue donate button right there on our main page. You can go right there. You can join us in 2 weeks on November 17th for a lecture by Nico Larco and Becky Steckler about advances in technology, such as the advent of autonomous vehicles, the rise of e-commerce, and the proliferation of the sharing economy, and how they are having profound effects, not only on how we live, move, and spend our time in cities, but increasingly on urban form and development itself. Sounds fascinating. Once again, a big thank you to Celestream for making tonight's event possible. And as always, check out our website, omsi.edu, for more info and some cool stuff. Thank you, everyone. We'll see you later.